Good morning. Okay, we're a bit thin on the ground. I guess it's a bit early in the morning still, but if you come from Europe, it's probably still quite late in the day, as I have. So I'm the chair of the Future Technology Symposium. I get the opportunity to speak to you first. But you've got my honorary positions there, but I'm actually from Research Institutes of Sweden. In Sweden, I work at RISE. What we can talk about first is the actual schedule for today. So the whole idea here is we have a couple of keynotes. We have a keynote speaker that we've invited, some sponsors, presentations, and then we break out into two presentations for the AI and HPC track, and then we'll have a break for the posters, followed by lightning talks, 5 lightning talks from the AI HPC track. And then we move on to data center sustainability. Again, the same format, 2 presentations and 5 lightning talks. And there is an award ceremony, so we've had quite a large number of submissions this year. And we had to, break it down into posters and presentations. And so there is the best paper, or the best overall paper, which has a prize of $10,000, which we'll present at the end of the award, the end of the session at 11:25. And then there is best paper in the DC sustainability track and best paper in the AI HPC track. There are some sponsors that will talk here, so we'd like to thank our main sponsors here, Samsung and Teradyne. But there's also an additional sponsor with a giveaway, and the giveaway, so Stefan is in the room. Stefan, I lost where he is, at the back there. When you leave, if you pick up one of these giveaway tickets, you can go to their booth and you can collect this, which is the US Constitution in this. You can't actually see it, but Stefan, maybe you do need to say something. Do you want to come to the mic there and just say briefly what it is? Yeah.
I don't know if this mic is hot.
Yeah. Yes, it should be hot.
So we thought a hands-on demonstration of an emerging capacity storage technology may be the perfect context for Future Technology Symposium. This is a ceramic data storage sheet that contains copies of the US constitutions as a reference text intended to be preserved for eternity, suggested by the US Library of Congress.
Okay, thank you, Stefan. Yeah, so an interesting thing. So if you collect one of the tickets on the way out, you can collect this US Constitution in this device. So I just wanted to say a few things, and I thought, what can I talk about this time? And I know we've been talking a lot about power. We've been talking about megawatts, gigawatts, bragawatts. Data centers are now consuming a lot more power. So I thought I'd actually have some reflections on the computing process itself. And I have talked to a lot of people about this, and forgive me if I'm a little bit provocative here, but I would like to go back to Richard Feynman and what he said in 1980, or in the 1980s. There was a book, a very well written book there called Lectures in Computation. In the last 10 years of his life, he was a physicist. He spent a lot of time looking at the computing process. And those diagrams are from some of his sketches, and his conclusion was engineers should be ashamed of themselves because we have a very inefficient process. And I want to talk a little bit about this process that is horrendously inefficient. Okay, we're doing great things with it, but it's just a reflection. And maybe I'm trying to be a little bit provocative, but we talk about flops. You will have seen this, zettaflops, yottaflops. I mean, the size of these foundation models now are tremendous. It's a huge amount of compute that's required to train them. But not all flops are the same. So I've got some equations here that how do you understand the compute efficiency? Well, it's the amount of compute you can do for the energy that you need to consume, because data centers are metered on the energy they consume from the grid. But you need to do that computation as fast as possible. So it's like you buy a Ferrari. You don't buy a Ferrari because it's an efficient vehicle. You buy it because you want to get from A to B as fast as you possibly can, if the law allows you to do that. And so it's not more about flops per watt that we talk about, which is the rate of compute divided by the rate of energy consumption. But there was some work done in the 1960s. Rolf Landau, another IBM fellow, he used to get cross with everybody who thought computing was just something you get for free. It actually consumes resource. We have to remember that. I think we know that today. But he actually looked at the computing process, and the paper was Irreversibility and Heat Generation in the Computing Process. And I've done a little calculation here. So if you break it down into its elementary form, you've got 2 states before you go through the logic gate, and you've got 1 state when you come out of the side of the logic gate, the other side of the logic gate. And Landau was able to say, well, if you use Boltzmann's theory for energy dissipation from that, going from 2 states, because you can get the entropy of the system with 2 states and the entropy of the system after, the difference is the heat that's dissipated. And so he was saying that the minimum amount of energy you need to dissipate with an irreversible computing process is 3 zeptojoules. How are we doing today? This is some graphs of how we're doing today. So on the left there is quite an old diagram, and that's looking at the amount of energy dissipation per transistor. Sorry, excuse me. And you can see that it was going down. That's a log linear plot. You can see it was following a line straight down to the lambda limit. The lambda limit is at the very bottom there, the dotted line at the bottom. And now we're sort of coming off that curve now because we're challenged by a lot of physics. We're having an interesting conversation this morning about not being able to break the laws of physics. You know, that's the unfortunate thing. So it looks like by 2030 we'll get to 1 attojoule. So that's still 300 times more than we need than the lambda limit. So you know, we've still got a long way to go. But will we ever get there? That's the question. On the right, I want to point out the fact that not all flops are the same. So when you see presentations and they say that the supercomputers today are much faster than the supercomputers of yesterday, or some of the scientific supercomputers, those scientific computers are running with double precision. So it's FP64. But if you halve the precision, you halve the amount of energy that you need to consume to do the compute. You halve it again, and so on. And so we're in a situation now where the flop that's being presented is 8 bits, not 64 bits that we use in scientific computing. And so you cannot really compare the two. They're different flops. So that's something I wanted to say. But what does the future look like? I mean, this is and I thank Alan here for, over here, because this is not my area of expertise, but it's always good from the thermal side of things to understand where we're going with these microprocessors. So I did a little bit of research on this, and the total power consumed, say, by a B200. You can break it down to static, dynamic, and the I/O power. Now, I can be criticized for this, but I'm just throwing it out there as an ideal calculation here. So the static power depends on so you can see the red there is that's the number, that's the transistor capacitance, the number of transistors we have on these GPUs, the frequency, the switching rate, and the voltage of the supply voltage that they're operating at. And there's an activity factor, so how many of the transistors are you using at any one point in time. There's also a current leakage in the transistors, which is 3 nanoamps at 60 degrees centigrade approximately, and that actually increases as the temperature goes up. So you will consume more energy without even dealing with the compute itself. You will consume more energy if you operate hotter, which is something we're actually doing a little bit in data centers at the moment. And then there's the input and output, you know, getting the data into the processor and out of the processor. Anyway, there's some numbers there. You can look at those slides later. But if you do look at actually doing those back-of-the-envelope calculations and adding up the dynamic power, the static power, and the I/O power, you get something that is much greater than the actual TDP of the. Thank you very much. Yeah. So there has to be some kind of dark silicon there, and this is something that I've talked to a lot of people about. So not all of the processor can be alight at any one time because it's capped by the TDP. But the potential to raise that is obviously there. Obviously, this is just a back of the envelope calculation, but the interesting thing is that based on the transistor density that we've got for the B200, which is an N4P node, it's around about, if in a square millimeter, if you lit up all those transistors, you've got 2 megawatts per square meter of heat flux. 2 megawatts. The sun, the surface of the sun is 10 megawatts. So it's a fifth of the surface of the sun. That's what we have to deal with from the thermodynamic side. The other problem with we need a lot of memory right next to the GPU, so we're starting to stack this high bandwidth memory. And some quick calculations on that is that it's difficult to get the heat out of the vias, so the bottom layer is sitting on top of a lot of vias of silicon, and you've got to get the heat out from the bottom. So there's a limitation on temperature there as well. Something to think about. But interesting, this is from Anastasia Nosova, who gave a keynote at the Green Computing in the AI era this year. And she was identifying the fact that we're growing the compute performance is on a 1.3 times trajectory, but our demand for compute is on a 4.6 times trajectory. And the consequence of that gap is we need more data centers, we need more power, which is obviously what we're seeing. So that there's a divergence there. But I just thought I'd throw in there, just before I finish, some of the technology. She also, Anastasia also talked about this, but I probably can't go into this in too detail because I've got very limited time. But there is the energy estimates of the computing process on the right there. But we've got neuromorphic, we've got analog, we've got quantum, which is obviously reversible computing, probabilistic computing, superconducting computing. There are lots of different ways of doing computing. And sometimes maybe we should stop and think, are we on the right trajectory here with the enormous amounts of energy that's required to do computing? But the inevitable consequence of all this is that it will become heterogeneous, hybrid in the computing stack, because we need to use those components that do the specific tasks that we do. So probably a nightmare for a computer programmer at the end of the day. But the software stack that sits around that is most important. And on that note, I'd like to finish, because I need to move on to the next keynote. So I might have time for one question, if anybody has a question. It's too early in the morning. So a vote then maybe. Should Feynman's name be on the next generation of GPU? Given his quote, engineers should be ashamed of themselves. I'm on a campaign to get his name removed. It should be called the Edison, I think. But anyway, yeah, it's something to think about. But thanks for your time, and I'm going to move on to our next keynote. Okay, thanks very much.